In this video, I'm going to introduce this unit on mathematical modeling, which is a model of internet use over a wireless network. Now you can read this introduction. It kind of explains what's going on. Let me show you a picture. When you use your mobile phone talks to a base station. I'm sure you've seen the towers, the cell phone towers. And ordinarily, each mobile phone will get a dedicated channel. Now, what do I mean by channel? Channel is kind of like a link. If you've ever used walkie-talkies, then you know that sometimes you might be on the same channel as somebody else, and you can both hear each other. Now, when you're using your cell phone, you're given your own channel. Nobody else has that channel. The problem with that model is that it's limited. If I want to use internet over the wireless network, okay, so here I have my laptop. I'm using internet here. Now, if I have my own channel, then most of the time that channel is going to be unused. If you think about when you surf the internet, you load a page and then you spend several seconds or minutes looking at the page, and then you load another page. In between those different loads, the channel is completely unused. So that's very inefficient use of resource. So what actually happens is that different internet users share the same channel. And there's a sharing that's going on. Now you have to be careful about this because in my walkie-talkie example, the different users on the same channel could hear each other. And of course, when you're using the internet, if you're doing e-commerce and using your credit card, you certainly don't want anyone else to know what you're doing over the channel. So somehow the different users who share the channel still have their own privacy. However, the idea is that these different users are sharing a single channel. And if too many people want to use the same channel at the same time, they'll have to wait. So a system has to be worked out for sharing this channel. And this is called arbitration. Now, you have several users who want to use the channel at the same time. You need to choose between those who get to use right away and those who have to wait. So the system we'll be studying is a system for allocating this channel resource to users who are sharing it. Okay, so that's pretty much what the introduction is talking about. Now, you can see that we're talking about users using the same channel. There's some probability involved because who knows when someone's going to click on a different web address, or who knows how many people are going to want to access the internet at a particular time. So there's some probability involved here. So in order to use this model, we're going to have to use some probability concepts that you should have seen before in your undergraduate probability class. You may want to review. I also gave some internet references. The first one is uniform probability distribution. And I'll give a simple example. Suppose I want to choose a uniform, I'll say random variable on the interval 0, 10. Okay. Now, what is a random variable? I could just say that that's one particular type of random outcome. Suppose I have a spinner, and the spinner is labeled with numbers from 0 up to 10. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I spin the spinner, and I have some kind of outcome. Okay. Now, it's clear that any number in this case is equally likely. So this is a uniform random variable on the interval from 0 to 10. This is represented by a so-called probability density function. Okay. The probability is between 0 and 10, so I put between 0 and 10. So here's the value axis, and here's the density axis. Now, if the random variable is uniform, the density is constant. Okay? But the density has to be arranged so that the total area is equal to 1. Okay? The total area corresponds to the total probability, and probabilities always need to add up to 1. Okay? Now, if I want to compute probabilities of specific events, I can use this density function. For instance, suppose I want the probability that my random variable x is between 2 and 6. Okay, what do I mean by this? I mean, I spin the spinner, and I want the probability that the result is going to be between 2 and 6. Well, I put 2 here, and I put 6 here, and this probability will correspond to the area between 2 and 6. What's the area between 2 and 6? Well, it's going to be this length, which is 4, times this height. Now, what's this height? Well, I specified that the total area of the big rectangle must be 1, and the length here is 10, so the height must be 1/10. Okay, so the probability of being between 2 and 6 is going to be this length, which is, I can write it as 6 minus 2. And then that's going to be times the height, which gives me a times 1/10. So that's 4/10. Okay. Now this is how you compute probabilities with uniform random variables, right? Next is probabilities of independent events. Now what's an independent event? Let me give an example. Usual example is flipping a coin, or flipping 2 coins rather. I'm going to go farther, and I'm going to do flipping 3 coins. Okay. So on my first flip, I have heads or tails, and each has probability 1/2. On my second flip, I have heads or tails. Each has probability 1/2. On my third flip, I have heads or tails. Each has probability 1/2. So what's the probability of getting 3 heads? All right, now what you do here is you have probability the first head is 1/2, probably second head is 1/2, probably third head is 1/2. And these outcomes don't affect each other. That's what it means that they're independent. So if half the time I get a head for the first one, and half of that time I get a head for the second one, and half of that time I get a head for the third one, that's going to be 1/2 times 1/2 times 1/2 equals 1/8. Okay. This illustrates this formula down here, that the probability of independent events multiplies. If I want the probability that 2 independent events occur, I multiply the probabilities. Now, of course, I can extend that. I can say the probability of A and B and C is equal to the probability of A times the probability of B times the probability of C, as long as A, B, and C are independent events. Okay, so you should remember that rule. Independent events, their probabilities multiply. All right, next concept is expected value. That's almost like the mean value. And expected value is the expected outcome. So let me do an example. Let me choose a random day of the month. Okay. And I want the expected date. Okay. Is it 1, 2, 3? So here my month has 30 days also. I'll just say that. Now, what are the possibilities? I could choose the first day, or the second day, or the third day, all the way up to the 30th day. Those are my possible outcomes. Now, what's the probability of choosing the first day? Well, it's 1/30th. What's the probability of choosing the second day? It's 1/30th. Well, I'm going to multiply that by the outcome. Probability of choosing the third day, it's 1/30th. Fourth day, all the way up to 30th day. To get the expected date, I would sum all of these values together. Okay. Notice what you actually have here is the sum of the integers from 1 to 30 divided by 30. There's a formula for the sum of integers from 1 to n, and that would give me here 30 times 31 over 2 divided by 30. This divided by 30 is from the 30 in the denominator here. And that gives me 31 over 2. Now you might be surprised that the expected date is 31 over 2 instead of 15. You'd think that 15 is the average. But the fact that it's different corresponds to the fact I'm taking integer values here and I'm starting with 1 instead of 0. So you can think about that. This is very close to 15. But what I've done is I've taken each outcome and multiplied by its probability and summed the results together. That reflects the formula that is given down here. The expected value of an integer valued random variable is the sum of the possible outcomes times the probability of each outcome. Okay. All right, last one is a technical thing, summation notation. You should understand what this means. N equals 1 to 3. If I have p to the n, you should understand what that means. That's the same thing. Well, that's the same thing as p to the 1 plus p to the 2 plus p to the 3. You may also see something like this, sum from n equals 0 to infinity of a x to the n. You should know that that means a times x to the 0, but x to the 0 is 1, plus ax plus ax squared. Okay. So if you're not familiar with this notation, you should go back and review. The sigma represents a sum, and these limits represent the first term and the last term. Okay. So the formulas you'll need: probability of independent events. I've talked about that already. Probability of complementary events. What does complementary event mean? It means that B is equal to not A. Okay. So for instance, if you have the probability of rain is 0.2, then the probability of not rain should be equal to 1 minus 0.2, or 0.8. Expected value of an integer valued random variable, I talked about that before. The sum of integers from 1 to n, you should know this formula. In fact, you should memorize this formula. It's a very commonly used formula. If you don't know what it is, just Google sum of integers from 1 to n and remember that formula. Also, sum of geometric series. Okay, sum of geometric series has the form sum of a q to the n. Whoops. And sometimes you'll have an infinite sum, n equals 0 to infinity. Sometimes you'll have a finite sum, 0 to m. And you might use different letters. You might have bx to the n. Okay. You should know the formula for these geometric series. Both the infinite and the finite case. All right, here's another formula that you'll need. I want you to realize here, in this case, this sum is equal to, I can take the b out because it's a constant. It's b times the sum from n equals 0 to m of x to the n. So you need to know that you can take constants out when you're doing sum. All right, here's some other formulas that you'll need. This is not quite a geometric sum, but it's closely related. And here I give the finite version with a finite upper limit m plus 1. And here I give the infinite version from 1 to infinity. Okay, so those are the sums you'll need. And now we can start talking about what the activities actually are. Okay, the first activity is for pencil and paper. You can do it on paper, or you can use a Word document if you prefer, or some other text document. It doesn't matter, just so it's legible. But it's not for a spreadsheet. Okay, so in scenario 1, you're waiting for a taxi. For each given minute, there's a probability 0.2 for a taxi to pass by. Okay, so what do we have here? We have I can draw a number line. And I'm going to number the minutes 0, 1, 2, 3, etc. All right. Now, according to the way I'm labeling this, the 0th minute is the minute here. Okay. The nth minute, if I go out here and I take n and n plus 1, the nth minute is the minute between n and n plus 1. Okay, that's important because I might have chosen this first minute to be the first minute, but I'm choosing it as the 0th minute. Okay. Now P of 0 is the probability that the first taxi arrives in this interval. Okay, that one should be pretty straightforward. The probability that the taxi arrives in any interval is 0.2. P of 1 is the probability that the first taxi, now the first taxi, that's important. The first taxi arrives in this minute. Now, how is that possible? Well, if the first taxi comes in this minute, it can't come in this minute. That means no taxi comes in the 0th minute, and a taxi comes here. So this P of 1 is actually equal to, there has to be no taxi in the first minute, in the 0th minute rather, and then there has to be a taxi in the first minute. What's the probability of no taxi? Well, there's your complementary probabilities here. Here's 0.2. That's going to be 0.8. What's the probability of taxi? That's 0.2. All right, so I gave you the answer for P of 1. You have to reason out P of 2 in the same way. Okay, it's not written on this version, but I'm also asking for the formula of P of n. So I'm also going to ask, what is P of n? You'll have that on your sheet. So that I'll be asking for the general formula here. All right, for part B, I want you to compute some specific probabilities related to P of n. So you should be able to express this probability in terms of P of n for some specific values of n. Okay. All right, same with this and same with this. Okay. All right, now for part E, you want an expected number of minutes that you'll have to wait. All right, and here I want the, in this one I just want the formula. So you should use summation notation. Okay. And then in F, I want you to evaluate the formula. You'll use one of the sum formulas I gave in the previous section. Okay. Scenario 2 is for a bus. And again, we divide we're waiting for an hour. So of course, an hour is 60 minutes. And I divide this up into minutes. Okay. And as I said before, this first interval is the 0th minute. Second interval is the first minute, and so on. Okay. And here I want the probability of Q of n. And I want the probability, and I want you a formula for this Q of n. Okay. Now remember, only one bus arrives during the hour. So we don't have to worry about multiple buses arriving in the hour. Only one bus will arrive in the hour. And then here I want you to evaluate some different probabilities and also the expected number of minutes. And this one you get using the summation formula. Okay. In scenario 3, I want you to compare an alternative. You have a choice of taking bus or taxi, and they cost the same. And you're supposed to choose which one you should take. Okay. All right, so that takes us through these 3 scenarios. So this is preliminary for our real model, which is the random access channel. And as I said, this random access channel was pictured here. You have different users sharing one single channel. And the different users use it or not in a random sort of fashion. And let me try to explain this description in terms of the system diagram down here. All right, you should think about this as starting here. You start here. This means that you enter the system, and when you enter the system knows that you're trying to get in, and it puts you in the so-called back-off stage. Now, in the back-off stage, there's B00, B01, all the way up to B0, W0 minus 1. There are W0 different states within this back-off stage. Right? Look at these arrows. They're all labeled 1. Right? Here's B0, W0 minus 1. With probability 1, that goes to B0, W0 minus 2. So at each tick of the clock, I'm going to move from one state to the next state. Okay. I don't know what that time interval is between ticks of the clock, but I'm just saying that there is a standard time interval, and during this standard time interval, I move from one state to the next state. If you remember our model with spotted owls, that tick of the clock could be a month, or it could be a year, or something like that. But there is some time unit that determines the time that it takes to go from one state to the next state. Now, when I enter this so-called back-off stage, I could enter any one of these W0 states. The probability that I enter a particular state is 1 over W0. Okay? So for instance, if I had 3 states, if I had W0 equals 3, W0 equals 3. It's possible, in that case, I would have 3 states. This would be B01, B02, B03. And the probability of going to any one of these would be 1/3. Now, once I'm into the back-off stage, I move to the left with probability 1. So for instance, if I enter the system in the middle state, on the next clock tick, I'd move here. Then on the next clock tick, I'd move out of the back off stage. All right, so that's the back off stage. After the back off stage, you enter the wait plane. Now there are two possible queues, as it were, that you can enter. You can enter the top one where the states are labeled X, or you could label the bottom one where the states are labeled Y. The probability of going into the top line is 1 minus P. The probability of going to the bottom series is P. And notice these probabilities add up to 1 because you'll either go one way or the other way. Right, so after you leave the back off stage, you enter the wait plane, and there are basically two lines that you could be waiting in. In this line, you just move to the left, to the left, to the left, to the left, and then out to the next stage. What does that mean? That means that at the first stage, or the 0th stage rather, you have failed to gain access. How about if you make to the upper line? Well, in the upper line, I go to the first state here, which is x00. There's a probability Q that access will be granted. And that means I do get to use the channel. There's a probability 1 minus Q that I don't get to use the channel, and I have to wait. Then the same thing happens here. At this state, then there's a probability Q that I get access granted, 1 minus Q that I don't. And I get passed down the line here. Once I read the last stage, there's a probability Q that I get access, probability 1 minus Q that I'm passed on to the next stage. And the next stage, things happen all over again. Here's the second back off stage, and here's the second wait plane. Now notice there's an arrow going off down here that's not going anywhere. We don't worry about that right now because we're only concerned about this part of the system. Right, activity 2 only concerned about this part of the system. Right, so that's a short introduction of what's going on here. Now these circles are just like these circles in the system diagram for spotted owls. These are different states that the user could be in. For spotted owls, the spotted owl could be a juvenile, subadult, or adult. In this case, the different labels are different, but the idea is the same. User can be in the first state of the wait plane or the first state of the back off stage, etc. Notice one thing that's a little bit tricky here is that in the wait plane, how many X's are there? Notice you're starting to count at 0. So it's x00, x01, blah, 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 up to x0m. How many X's are there? Think about it. There's actually m plus 1 X's in this series. Here we have W0, different possibilities for B. But here we have m plus 1. Okay. All right, so here we do some questions about this system. Some of these are easy and some of them require computation. Okay, some you can just get directly off of the diagram, and some you'll have to figure out using the information there. Okay, so what's the probability that the SS request is acknowledged in state B00? SS is that's shorthand for subscriber station. What that just means is the user. So what's the question asking here? What's the, it says if you're in state B00, what's the probability that your request will be acknowledged, which means what's the probability that you're going to go up here? Okay. Let's look at B. Suppose the subscriber station request is acknowledged in state B00. Then what's the probability that the subscriber station will be granted access from state 0? The hint is sum up the probabilities of all possible ways that access can be granted. Okay. So I'm saying here that the subscriber station request is acknowledged. That means that I've gone up here. I'm going to the upper line. And what is the probability that I will be granted access? Well, at first I'll be here. What's the probability that I'm granted access from here? Well, I could go directly to have access granted. That would be probability Q. Okay. But that's not the only way I could have access granted. It's possible that I could be passed down to here, and then from this state have access granted Q. What's the probability of that option? Well, the probability of going from here to here is 1 minus Q. The probability of having access granted from this state is Q. So that's 1 minus Q times Q. Okay. It's also possible that I go 1 to third state. From the third state have access granted. What's the probability there? Well, I would like you to figure that out. But notice that the probability of being passed along is 1 minus Q. And then once you reach the state and have access granted, that's Q. So you're going to have this times Q. Right. Now what I'm asking here is the total probability that by the time I finish with this line, I'll have access granted. Okay, so that's what I will want you to do. I'll give you a hint. There's an easy way to find this without doing the sum if you use complementary probabilities. But you can also use a sum. Okay, this question C asks if the SS request is not acknowledged, what's the probability that you'll be granted access? So this is talking about the case where after state B00, I go to the lower line. Okay. Then part D says, what is the overall probability that the SS will be granted access from stage 0? Okay. All right, now be careful here. This is not just the sum of probabilities from B to C, of B and C. Why is that? Because here I'm not assuming that access is granted or access is not granted. You also need to take into account that a certain proportion have access granted and a certain proportion do not have access granted. Okay, so you can do this problem the same way that you did parts B and C by summing up probabilities. If you see the pattern, though, you can make this problem somewhat easier. All right. Now, so part E is just asking about for some observation in the diagram. So here it says, what is the longest time that the user can remain in stage 0 backoff? And what's the shortest time? And then here I'm asking for what's the expected time. Now here, again, we have the expected time of waiting is going to be an integer. For instance, if I go into the backoff stage and I enter here, the expected time in the backoff stage is going to be 1 because I'll go into here and then I'll go out immediately. Okay. If I go directly into the second one here, the time in the backoff stage is going to be 2. Okay. So you can see actually there's W0 possibilities here. And you're going to have to sum up for these possibilities using the expected value formula. Okay. Let's see, where are we? Okay, so this is asking for the expected time in the backoff stage. This one is asking for the expected time in the wait plane if the subscriber request is not acknowledged. And this one is a little more difficult. This is to show the expected time that the user will stay in the wait plane if the request is acknowledged. So H is talking about the case where you enter the wait plane and go in the lower group, the lower series. And the last problem is talking about the expected time if you go in the upper series. Okay.